So here you can see that the entrance region, it depends on your Reynolds number, okay? And the formula for that we have here, okay? So like I can, and this is the formula is only for the entrance region. For the remaining region, that we can like create some length, okay? So to decide first, because we need that the flow should be fully developed, it should not change its properties, and so that we can analyze the only heat transfer. Okay, if both things are changing, like flow physics and the heat transfer is applied, so we cannot say what is happening. Okay, so somebody makes the pipe length of 10 meters, he will get the different results of the heat transfer Nusselt number. Somebody who makes a pipe length 100 meters, he will get different results. So that's why either you should make a very long pipe so the flow is fully developed when it reaches the heated region, or you should make the you can apply the shorter length, but then you have to apply the fully developed flow on the inlet of the pipe through UDF. Okay, UDF is a C++ or C program, and it's a stand for user defined function. So it adds a functionality into the Fluent, which we cannot we cannot get the everything in the Fluent interface, that because there are the very vast world of fluid dynamics and heat transfer. So a Fluent interface cannot provide you everything specific to your problem. So that's why they added the functionality that you can add your own functions and you can enhance the its usability. Okay. So now I just slightly changed the now flow problem, and it actually makes the problem understanding better. Okay. So previously, what we did is that let me recap. We did the geometry making, we did some basics, and then we made the high quality examination. So I'm not going to go to that part, but I will show you that if the geometry change, then how I can use the old blocking with the new geometry. Okay, that I will show you. But let me go through the like this part. So I changed some properties here. I put the heat flux of 5,000 watt per meter square. I put the viscosity as a 0.001 and density as a 1000 kilogram per meter cube. This is the properties for the water. Okay. Previously, we were solving the problem with the air. So water or air doesn't matter. What matters is the Reynolds number. If this is same, then we should be getting the similar properties, similar results. Okay. Same results in nine-dimensional form, and the trend in dimensional figures should be similar. Cannot be same, but it should be similar. Non-dimensional quantity should be exactly same. Okay. And also I add the properties, some properties I modified. So CP for the water is the 444148. So I just made it 3000. And why? So I will explain that thing, because I wanted to match the Prandtl number within the some range. Okay. It still is like a slightly different, but I wanted to make it a little bit lower. So that's why I changed the CP from 4148 to the 3000. And the thermal conductivity of the water is like a 0.06. So I made it 1.5. Okay. So again, the point is that if you are matching the Reynolds number, you are matching the Prandtl number, and you are using those values in the correlations, and then your CFD and those correlations values should be same. Even if I run the simulation with a slightly different value, let's say I'm running simulation with the 1.2 and the CP as the 2800. You are running with this value, and but our Prandtl number and Reynolds number are same, then we should be getting same Nusselt number. Okay, clear? So it's clear that matching these non-dimensional parameters ensures that we are going to get the similar results. Okay, so you must pay attention here to match these non-dimensional parameters. That's the purpose of these non-dimensional parameters. Okay. So if I don't model my pipe with the help of the velocity profile through UDF, then just to imagine that if I'm going with a 10K to the 150K Reynolds number with a 10K with this correlation, my entrance length and keeping diameter is equal to 1 meter. So put the Reynolds number here, multiply power 1/6 and multiply the 4.4. This gives us for 10K, the entrance region means this blue region length of the pipe should be at least 6.4 meters. But if you go to higher Reynolds number like a 150, 150 is not very high in terms of the turbulent flow, but it's still high enough. So the length of pipe we have to add here is like 32 meters. Now imagine that if you double the value, this will be like maybe 60 plus meters. Okay, so this will require a lot of mesh elements to be there, and this will require a lot of time to solve the case. Okay, so that's why what I did is that I shortened my domain to the made it 5 meters, and my heated region is 20 meters. Okay, that's all. Okay, so we made these based on this analysis of the entrance length with the Reynolds number. So I propose that we can shorten the domain length, and it will shorten our simulation time, our RAM requirements, our CPU requirements, our hard disk requirements, because it will save the file with a more mesh, means that the size will be bigger. So we can save that if we apply the velocity profile using the UDF. So I will explain what is the profile for the turbulent flow. For laminar flow, we know that is the parabolic velocity profile. For turbulent flow, it's slightly different. Okay. Now for turbulent flow, if you go through literature, through the papers, through the books, they will show you that the fully developed turbulent flow profile will be like this. Means that there will be like a very steep gradient on the wall, and there will be like a very little change in the middle of the domain, like 80%, 60% of the whole domain. Okay, now similarly, if you take a look on the laminar flow, it's a more smoother. Okay, so what we were discussing previously here, that we wanted to make sure that flow is fully developed. So either you should provide the enough length in the pipe, or you should apply the velocity profile. For example, this profile, if I make the length shorter here up to here, and I simply apply my velocity profile like this one. Okay, this is a 1/7 law. Okay, if for turbulent flow, n value is a 7, that's why it's called a 1/7 law. So you know that the u upon u maximum is equal to 1 minus r upon r power 1 by n. So I can write down this equation as the u as a u of r or u of y, whatever you are saying this one. So this is equal to the u maximum into 1 minus r upon r power whole power 1 by n. So this n is equal to this n is equal to 7. Okay, so now for this case, what we can do is that now we have to find out the u maximum. The u maximum are given, generally speaking. What we are given the velocity, uniform velocity at the inlet. So that velocity is actually is also called the u mean or u average, because if you average the velocity, different velocities here, and you will end up with the same velocity as the velocity we have here. Why so? Because flow rate here and flow rate here cannot be different. So it means that the every velocity here, every velocity here should be same. Okay, but because of boundary layer, the velocity here will be of the no slip condition, velocity will be 0, but in the middle velocity will increase too, so that it can have the same flow rate at the different locations, because mass should be conserved always. So from there, we can say that the every velocity here is like this one, and this is our maximum velocity. So this is the u average or u mean, and this is the u maximum that is in the center. So for this problem, what we know that for this problem, the velocity, every velocity becomes the u maximum in terms of the every velocity is equal to 1.2245 times the u mean. So I provided that velocity, this function into UDF, and UDF is here. Okay, so if I explain the UDF, so you can see that this UDF tells you about the first. You can put some comments. Okay, so this is I specially made this UDF for this course. That's why you can see the name of the course here as well. Okay. Secondly, now if you take a look here, first we have to put the mandatory command that it will use the built-in library, UDF library. So this function is coming, these functions are coming from those built-in libraries. But if those functions aren't there, you have to make your own function, then you have to provide that function library name here. Okay. So I'm defining my u average as the 0.01. So 0.01, it's coming from the calculations. I will show you those ones also. And the radius of the pipe is 0.5 meters, because that the diameter of the pipe is equal to the 1 meter. So its radius would be equal to half, which is the 0.5. Then this is a built-in command for the defining the velocity profile or any profile for turbulent also. So we are defining the one array of a velocity. So there's a pipe face here like this one, and this will on if you divide them into radial lines. So this will look like in this way. So on these radial lines, the velocity will vary from with the help of like a function here, that is the from this here r is equal to 0 and here r is equal to r. So velocity here they will be exactly same. So if I draw the some like angular bands here, so on these angular bands, the velocity will be exactly same. Okay. So it means that we if I apply the velocity profile on the any x and y combination, and if the value remains same, like radius is same, so that the x square y square same, so that we should be having same value of the velocity there. Okay, here or here or here. So in this way, we applied the velocity profile so that we get the minimum velocity on the wall and maximum velocity, that is the 2 to 4 5 times of the u mean on the center. Okay, and because we know that the once the flow is fully developed, then this velocity profile will not change, but there will be some little changes because of turbulent flow that might not be matching with this velocity profile. So this will be some little changes, and that's why I provided the 5 meters length so that it can compensate quickly within that range. Okay, and then we have the 20 meters length for the heated pipe where we can analyze the heat transfer. Okay. So we have now applied some built-in commands here. So real F, real R radius, real F, FTF. So this is the indicator, phase indicator. Okay. So first I'm defining the U maximum, which is equal to the, because you know the U average, but we never know the U maximum. U maximum is because depends on the U average. So that's why I provided a U average in the very beginning. You can change it also depending on your conditions. So we have the 1.2245 into U average. Then I put the loop here, and that loop will run on the all the faces, means all the cells or the nodes, cell centers on the that face. So it will look for the F cell centroid of the each and every mesh cell on the surface. It says this they are going to be the surface elements, not the volume elements. Okay. So R is the square root of x into x, means x square plus x into x, means, so this x actually the x0 is equal to the what? This x0 is the x. Okay, this x0 is the x. So this is the x into x square plus x1 is a y. So this is a y square. So it only says that the r is equal to square root of x square plus y square, r this term. Okay. Now, if the my length is actually is in this pipe is along the z-axis, so my phase will have the x and y. But if the my length was of the pipe was, let's say, is along the x-axis. Okay, its length is along the x-axis. So my this surface will be along the what? Along the y and z. In that case, what you have to do is that you have to provide the x1, that is a y, and the x2, that is a z. So here you will write the x1, x1, x2, and x2. This will be the y square plus z square. Okay. In that case, the radius would be equal to the under root y square plus z square. Okay. And then finally, we applied the profiles. This is the u maximum. U maximum is equal to this one. And this is equal to the 1 minus r upon r power 1 by 7. So this is the power formula. So this is saying that on this function 1 minus r upon r, put this power. Okay, this power is a 1 by 7, 1 by 1.0 to make it floating, 1.0 divided by 7.0. Okay, then we have the end loop, and then we have the end of this whole macro. Okay, any questions? Any questions?
Hi, Sijal. Yeah, I have a question. So, suppose you have a geometry with, let's say, two different velocity ranges. Let's say the inlet of the velocity is, let's say, 100, and the outlet is 300. Right. So, which velocity would you take into consideration?
Where?
I'm not talking about this particular case. Let's say there are some other cases which would have velocity. So, for example, for the first layer height calculation, so this for earlier steps.
Actually, this is only applied at the inlet. So means that we are talking about the inlet part only.
Oh, okay.
So
So we consider the let's say the Y plus calculator. We consider only the inlet velocities
no, no,
there.
no, no. For that, I'm going to tell you about the why how going to use the y plus calculator. And y plus calculator
Okay.
depends on the only the every velocity, not on the these velocities, the local
Oh,
velocities
okay.
which are varying there. Okay, it only
Right. Yeah.
depends on the mean velocity. That the mean velocity means when we talk about the mean velocity or any length or any velocity or anything for that sake. So those are actually the reference conditions. Okay. So length would be the characteristics. Length means that the length that is going to define the character of the flow. Okay. So for example, in case of the like aerofoil, the characteristic length will be the chord length. In case of the wing, tapered wing, proper wing, the characteristic length would be the mean aerodynamic chord. For the pipe flow, the characteristic length would be the diameter. For the vehicle like MS body, its height would be the characteristic length. Okay, so it depends. Similarly, the velocity that is that means those conditions which are not going to be changed. Number two is going to define the flow character. Number three is that they will be there always. For example, for the case of the uh, like any simulation, so inlet velocity is the velocity that will not change. Okay, for example, for the 40 meter per second, for MS body, for pipe flow, 1 meter per second. I'm just saying the numbers. So numbers, whatever numbers they can be, but those numbers which will not never change, whatever happens inside. Similarly, like we are now going to solve this case. So we are talking about the like a bulk temperature. Why bulk temperature or the mean temperature? Because that does not change locally. Okay. So what about if the flow was external flow? In external flow, our bulk temperature calculation would have been very simple. Why? Because in that case, I would provide the my inlet temperature condition to the problem. Okay, that is because that is my reference temperature that will never change. So I can rely on that temperature. Okay, but if in the internal flow, I cannot rely on the internal in the inlet temperature because inlet temperature will go through the lot of variations inside the boundary layer. So for internal flow, I have to calculate that temperature on that location by myself. Okay, so like it's a like a more than the like a CFD. It's a it goes towards the basic fluid dynamics. If you go through the basic fluid dynamics and see what numbers they are taking for reference conditions. I'm not talking about CFD. I'm talking about the general fluid dynamics heat transfer. So what they are doing for their calculations, like if I take the calculation 50 years ago, at that time we didn't have any CFD. Okay, so just see that what they are doing. So exactly same we have to do in the CFD because will be comparing are those methods are reliable. They know exactly what values they are looking for, how to find them. Only thing is difference that now we can find out those values with a much easier way, in the much easier way and very in a, like a less time and with a less cost. Okay, even if you go back to the 30 years 10 years ago or 20 years ago, the making geometry and then meshing was a very big task. Now everybody can like go to the some CAD software, then design, then the space claim it, he can clean the geometry, create the domain boundary condition, then quickly create the mesh in the answers meshing. Not very good mesh, but it's still the mesh. And then he can run the simulation. He knows from the very sources, okay, I need the y plus this one and this one. Even without knowing this one, they know y plus should be one. Okay, so once they make sure these things, they can run the simulation, they can get some decent results. But this was not the story 20 years ago. This was a very difficult thing to do the CFD. Okay, anyhow, so this is about the only this only concern with the we are making the domain very shorter. For example, if I'm running a simulation on the diffuser, okay, wind tunnel testing on the diffuser. So what they'll provide is that they will provide some settling chamber ahead of this diffuser. And secondly, what they do is that they provide the treatment on these walls, suction sort of thing. Okay, so they provide suction here so that there will no boundary layer is being made on the settling chamber walls. So that when flow goes into the diffuser, there is a very clean flow. Okay, so only variable that we are going to be monitor is what is going to change inside the diffuser, not what is going to happen before that. Similarly, in the CFD, what we do is that we do the same thing either by making this as a slip condition, means the zero slip or zero shear, and to apply the boundary layer directly, like if when the flow fluid develop, that we can do it using the UDF here. So we cannot do it directly exactly on the like a geometry entrance, because the flow will be changing here much more here, like its local condition changing. So it will mix out again, and we will never know what is going to what is the effect of the air. So we wanted to like separate the effects of the different things there. That's why I put some short length and put the UDF there. Okay, instead of having the very long length. Okay, this is only concerned with the constant length pipes, not with something else. Okay, clear? Okay, so we actually shorten the domain length. Like if I'm going with a big, larger round number, then I have to be having the very large length. So which I reduced. Okay. Then previously I had the very fine meshes, and I thought this is not required. So because length is also shortened, so we don't require the very less high number of cells. So I just made the three meshes. I will share with you. I'm working on only one mesh. I will share with you these two meshes and run these cases and see how much error you are going to get. Okay. And one more thing. This should go before this one. Okay. So what I did is that I slightly changed the values. So I changed my Reynolds number is same 10,000 initial Reynolds number. Viscosity is now is the viscosity of the water 0.001 Pascal second. Okay. Then diameter is the same 1 meter. Density is now 1000 kilogram per meter cube. So if you calculate the velocity now, the velocity becomes the velocity you can solve for velocity. So the velocity or u mean will be equal to the Reynolds number into viscosity divided by density into diameter. So it's a 10,000 into viscosity is a 0.001 divided by density 1000 and multiply with the diameter is equal to 1. So we get the U maximum is equal to 0.01 meter per second. So definitely the U mean is a 0.01 meter per second. So U maximum would be the 1.224 times, 5 times of the U mean. This becomes this value. Okay. So this is just for the confirmation. Okay. Now this is our mesh. And how I did the like first cell height. First cell height I made through the if you go through this training here, okay, and I will share you there's the same Y plus calculator I use in the MS body simulation. So here I just put the values for our case, simple. Okay. Okay, so what I did is I put the Reynolds number is equal to 10,000. I put the Y plus requirement as a 1. Density is a 1000, viscosity is a 0.001, velocity 0.01, and I got my first cell height to be the 0.0014. So what I did actually is that I put the value as the 0.001, okay, not 0.00145, but other some smaller value 0.001, okay. So let me show you the what values I'm getting in simulation. Just to show you, I will go through the whole case again, okay. So turbulence and the Y plus value on the two walls, okay. So value we are getting is very less, like a 0.1, okay. And I would suggest that you should not be doing that thing, like going to the very low values, but also at the same time, I would think that this is going to be okay. Why? See, this may be like looks like a random like approach here, so please bear with me, okay. Means that I'm jumping here and there, so just bear with me. I just wanted to show you one thing. For example, if I draw the one line, okay, so line at the x is equal to 23 meters, okay. So z is 23 meters, and sorry, yes, z will be 23 meters. So I'm going to draw the one line at a z constant z, but I will vary the y. Okay, so y will vary from minus 0.5 to plus 0.5. Okay, and x will be 0 because I'm doing it on the x0. The line will be along the y-axis only. So zx will be 0 here. So y will vary from minus 0.5 to plus 0.5. And here the z will also be constant. So means that second point, which is on the bottom, its value will be 23. And same goes with the point on the top side. So this is a radial line where we're going to draw the velocity profile. Okay. So click on the create. And if you draw the your geometry here, and view menu, compose. Okay, I'm just making it them as the visible ones. Okay, so put the 80% visibility or 90% visibility like that. Apply, and the heated wall then. Okay, okay, okay. I'm going to display now the only the this new line. Okay, x 23 meters. This line is here. Okay, this line. So let's display the vector plots here. And also if I want to display one more thing I want to display here is my center plane. And that will there will again be at the x0. Okay. So this is my like x coordinate 4. Okay. Create. So vector plots and display that one on the x coordinate 4. Okay, let's make it 0.6 maybe. Okay, now you can say here, or you can see here that this is resembling to the same profile as I was talking here, this one. Okay, if I put them side by side, okay, anyhow, just keep it as it is. Okay, so you can see that the velocity profile shows the same behavior. Okay, the velocity profile shows the similar behavior. So we have the like a very sharp gradients here. Okay, we have the sharp gradients here. Okay, so with the sharp gradients here, you can see here, and then the velocity changes to the some constant value, and then it's almost like a flat surface. Okay, like you can see here, similar behavior. Okay, so any questions? Okay, this is about the our velocity profile. Okay, second thing that I want to draw is temperature, and you'll see that the how thermal boundary layer is behaving here. So I'm going to draw the on the same line. Let's change the variable here. Okay, so I'm going to draw the temperature. Sorry. Okay, make it on the on the x-axis. So this will be along the y-axis. So 1 minute. Okay, this one. Okay, let's delete every other surface. Okay, so I'm going to delete these lines from here. Okay. Okay, that is going to be displaying like you're displaying the velocity along this axis. Okay, so velocity magnitude and okay, so we have the velocity like shown here. Okay, so here is the position and here the velocity. Now, if we talk about like temperature, the temperature will vary in this way. Okay, because we have high temperature on the surfaces and low temperature will be inside. Okay, we can see the bound layer is like smaller for temperatures compared to the velocity. So velocity bound layer is thicker than the this temperature boundary layer. Okay, so for to like cater for this thing, for example, now this very important thing that if you talk about the y plus 1, so the bound layer for the velocity was like this one, sorry, in this way. Okay, this has a, like up to here. So it means that the bound layer is like a thicker for the this is thickness is almost this one. Okay, in this case, temperature case, this thickness is almost like a here, lower than the velocity boundary layer. So it has to have the small cells so that it can capture the thermal boundary layer very well, which is also it is doing here. So that's why keeping the y plus around 0.1 is a maybe a good strategy. Okay. Okay. So any questions further? Any questions?
Sijal,
Yes.
can I have a look at you know where you defined the temperature on the boundary conditions earlier? Because I think I
Yes,
missed that
we are
one
going to
last
do
time.
the same thing, but I'm going to
Okay.
show you that what we defined here. I just defined the two walls. The one wall is here. So one wall is the non-heated wall that is like in the beginning, which is here. Then the second wall is the heated wall. So I defined only that one thing that the heat flux 5,000 watts per meter square. Okay, clear?
Yes,
So
thank you.
so what it's going to do is that it is going to provide the heat flux. Okay, here 5,000 watts per meter square. Now, what does it mean? It means that the actually the Q is equal to, if you talk about the conduction, Q is equal to the Ka delta T. Okay. If you talk about Newton's law of cooling, means convection, then it's H A into T1 minus T2. All right.
Oh, okay. But
Okay.
what happens, sorry, what happens if, let's say, instead of defining the heat flux, you define the temperature instead? Can you do that, or
Okay,
would that be
okay.
different?
What happens at number one is that I think that's an analytical solution for as far as I know, because I did it myself in my coursework, that we don't have any solution, analytical solution for the constant temperature uh, problem. Analytical solution. I'm not talking temperature. Secondly, when you talk about the constant temperature, what does it mean? What do you think?
Constant temperature, I believe that's, let's say, the wall temperature, isn't it? Not the reference.
See, wall temperature or whatever it is, it comes from
Yeah.
the some condition. For example, I have the bike. Okay, I have the bike engine. So there's an engine here, and outside I have the fins. Okay, I have the fins here. Okay, now if I want to analyze this problem, okay, this is the bike engine, single cylinder engine here. So I want to analyze heat transfer in the fins, how much heat transfer is taking place here. Okay, so whether it's cooling my engine or not. So what we are providing here, sometimes for solution purpose, what we do is that we provide that our temperature here is equal to the 1000 degrees Celsius, for example. Okay, very common thing. But you know that this one component temperature is coming from the what condition? It's coming from the equilibrium condition, that whatever heat is being generated here. So now see, this is producing some watts of energy, this engine. Okay, you can convert the horsepower to the watts very easily. So 1 kilowatt is equal to, I think, sorry, 1 horsepower is equal to 745 watts. Okay, so I can convert the 1 horsepower to the horsepower to watts, and watts to the horsepower. Okay, so now we know this thing. So now what we can see here, that there's one surface here. That surface will have some like a watts per meter square. Okay, so like this is like a you are cooking your food on the stove. So you are providing like heat on the bottom side, and that heat is in the constant rate. Okay, the Q is on the constant rate. What is going to happen is that if you like you cannot dissipate the heat from the top side through conduction or through convection, mostly the convection, natural convection. If you cannot dissipate the heat from the top to the surrounding, temperature will increase inside the like in the inside the this whatever it is. Okay, now this is example of pressure cooker. Pressure cooker, what is happening, that we put the some lid on the top of the pressure cooker, and it contains everything inside. So suddenly it is there, a temperature will also increase because of the the high pressures. So its boiling point temperature increases actually. Water's boiling point temperature is 100 degrees Celsius. It increases to the high temperatures. So it gets a more energy, it gets a more energy, it gets a more temperature, and that's why it cooks like very very quickly. Okay, 1/4 or 1/5 times of the natural the normal cooking. So this is like a the some so this temperature comes from the like the energy is going in, and then some cooling is happening here. So this cooling is producing like this dissipating the heat, and then finally equilibrium. In the equilibrium, what we get with we get some temperature if we measure with some thermometer. But if the fins are more efficient, the temperature may go to the like 800 degrees Celsius. If it is not efficient, temperature may go up to like a 1500 degrees Celsius. So this constant temperature is actually is one of the equilibrium conditions that is being applied there. But the heat flux here, that is like a design value, that is from the some mechanism, some device. We have some heater, that heater will produce some energy in the watts. Area of the that equipment, if we divide that energy with the area, we get the heat flux, watt per meter square. That's a more natural boundary condition for the heat transfer problem. Okay, but you can do it, but in that case the temperature will remain constant of the wall, and only this will increase temperature inside the pipe here. The fluid temperature will increase. Okay, and in the equilibrium condition, the fluid temperature will reach the temperature of 1000 degrees Celsius. We are providing 1000 degrees Celsius on the wall. Okay, so you can try that thing. All right, so now we start from the very scratch. So first thing that I want to show you, that how you can like for example, I have the this geometry with me. Okay, first thing is that we already made the mesh yesterday. I just want to show you one technique, one trick here, that if I change the geometry, then how I can work with my old blocking. Okay, any questions? Okay, let me open the my geometry here. Let's say this is my test case. Okay, I'm just changing geometry. So test. Okay, so I will just use the pull command and change the geometry here. So just changing the length. Okay, maybe you can also change the diameter as well. So change the length here as well. Save the file. Open the first file for the, sorry, not this is the tint file. I need the project file here. Okay, so open the project file. Okay, and let's say this is save as, save project as. So this is also test project. Okay, so I will import the geometry, import model. So now my new geometry now. I will process the name selections. Are you with me? Are you getting it, or are you getting bored? Okay. So I have the my now blocking is slightly different and the geometry is slightly different. Okay. Like this. Okay. So what I'm going to do is that first I'm going to delete these material names which are by default created by the ICEMCFD. So what I'm going to do is that I'm just going to change my blocking to suit my geometry. Okay. My blocking is here. My blocks are here. Blocks are here, and my geometry is here. This face and this face here. Okay. So what I'm going to do is that I'm going to work on this blocking so that I don't need to make the new blocking. Even my pre-mesh parameters are saved there. Okay. So I will just adjust to my new geometry. Maybe I have to change the number of cells along the length because length is now different. So we have to add some more cells there, but that's all. Okay. So what I'm going to do is that I'm going to use a set location, like a move vertex as a second command, and I will use a screen option. Screen option means that I can now choose my point. Okay, otherwise I can only choose the vertex. What is from the blocking and point is from the geometry. Okay, so I'm referring to geometry and I want to extend my blocking based on the Z direction up to here. So I will select all these vertices and I will simply click on the okay. Okay, apply. Similarly, I will select my one point on the circle on the second end. I will choose the vertices with the box selection and apply. Okay, that's all. Now I will associate them on these two ends and then we are all set. Okay. In the middle, if you want, maybe this is on the safer side. So I will do that thing as well. And then this end only for the outer edges, which are referring to the our geometry. Okay, that's all. So display the pre-mesh and so we right click here on the pre-mesh and convert to another mesh. That's all. So now we made the mesh on the new geometry. Very simple. Okay. Any questions? Okay. So now what I'm going to do is that I'm going to open the very fluent, fresh Fluent copy. Okay. We start from the very scratch. Okay. So close everything here as well, and I will just be reading the new our first mesh file. There are three mesh files: mesh one, mesh two, mesh three. Those are the coarse, medium, and the fine mesh. So read the mesh file. Okay, and make it all files. So sorry, this is here. Okay, this is a mesh number one only. So I just exported only one mesh, but all three files are ready. So here, and I'm going to choose the double precision and the four processors. Okay, and if you take a look here, what I did is that I made the three meshes. One is a 48,000 cells, then one 10,000 cells, and then two 43,000. So this is like a progressively doubling the size every time. Okay. Okay, first of all, I will define the material, my material. Okay, then I will discuss about other things. Okay, so define new one. So create edit. Okay, and I will go with the Fluent database and I will choose the water liquid. Okay, and click on copy, close, and close. Secondly, because already the field was air, so the my domain sales zone, they are referring to the air. I have to change them to the water first. Okay, so change the water liquid and apply and close. Okay, now go back to materials and double click on the water. Okay, so also we need to solve the energy equation. So from the models, I will turn on the energy equation because it's a heat transfer problem. So energy equation, and this will give me some properties here. Okay, so let's make it density as a 1000, viscosity as exactly 0.001, and I'm going to put the thermal conductivity. I will explain why so, but just do it right now. Just change it. So I'm going to put the my K. 1 minute. Just let me confirm. 0.001 into 3000 divided by 1.5, it gives me the two Prandtl number. Yes. So the viscosity is a 0.001, density Cp is a 3000. It's originally is a 4000, but I'm just reducing this one. So it will not store the energy inside the water, but rather it will transfer the energy towards from the wall to the fluid. It will not store the energy there, but it will show you the temperature change. Okay, the Cp is higher, then you will see the temperature is raising in the fluid. If the Cp is lower, you will see the temperature raising on the wall. Okay, so if you increase Cp, you will see the more temperature change or temperature gain in the inside that particular liquid or the fluid. But Cp is lower, then you will see the high temperature change in the on the wall surface. Okay, so that's why I wanted to see some change on the wall surface. Otherwise, it was showing very little values. That's why I just made the trick here and I change it. Okay, and same is goes with the thermal conductivity. If I change the thermal conductivity to the 1.5 from the 0.6, it will show me the more heat transfer. Okay, and then the temperature will also rise. So that is like opposite to the Cp. So Cp is 3000 and K is the 1.5. So Cp is 3000 and the thermal conductivity is the 1.5. Okay, so change, create, and then close. Okay, now I will go to the models here, and here I will choose the. Now you can choose the SST model or you can choose other models. It's your choice, but I would first go with the K epsilon, Lazable, and enhanced wall treatment because Y plus is less than 1. So I will go definitely with the enhanced wall treatment and click on the OK. Okay, then we have set the everything here. I will now go to the boundary conditions. Okay, I will go to the cell and cell condition also said. Now I will go to boundary conditions, and I will now put the my inlet velocity here. That is equal to the point 0.01. Okay, 0.01. So 0.01 meter per second. 0.01 temperature on the inlet. I'm going to put as a 288. 288. Apply and close. Okay. On the outlet, I will be putting the same. This is backflow temperature. Actually, backflow temperatures. Let's put the 288 and click on apply. Momentum will be same. And secondly, on the heated wall, I'm going to put the my heat flux, which is 5000. Okay. In the method, I will keep the default settings here. Maybe I will change the turbulence to second order and energy equations to second order, and this will change to the green Gauss cell base. This will give us the better solution. Okay, in the monitors, I will put the a strict convergence criteria. So let's put it minus e power 1 power minus 20. Okay, so that it can run the case with the required number of iteration. It should not convert, it should not stop solution by reaching these convergence very easily. So I'm putting the some like a tough convergence criteria. Okay. Okay. And then I will initialize with hybrid method is okay. Okay, let's put the number of iteration to the 500 and click on calculate. That's all. Any questions? I want to know that from three of you or the other students who are going to watch the recording, that what do you feel about the heat transfer simulations? What did you learn here, or what is different than the what you think that should be the in that way? Like somehow we have some perception about the something, so like running the simulation and changing the parameters on our own, that like gives us the flexibility. But what we are doing is that we are abiding to the basic fluid dynamics heat transfer principles. Then the non-dimensional numbers should be same. That's a basic principle. Okay, so any thoughts about that thing?
Uh, from my side, so you know when you change the materials and you define. So let me just bring up an example. So you had when you define the air or let's say water even, and then you change the thermal conductivity. So what I've never really done that before, because for my particular scenario referring to, uh, I've just kept it as constant, and then in the viscosity I've changed it to Sutherland because I'm doing ideal gas one. But what's would you say is the difference really? Because do you think
Actually, I would suggest that the CP can be changed to Sutherland because that will. But what I have done that thing also.
yeah.
But in Sutherland, you know that there are three coefficients, two coefficients. Okay, so we
Hmm.
have to provide those ones. So what
Oh,
I do
okay.
is that I will be keeping the my minimum like reference conditions, like maybe if I'm putting the my reference condition right now is a constant values, and my viscosity is let's say 0.001. Okay, I put the
Okay.
temperature and the viscosity corresponding to that condition, the first point. The second, third point, they will be depending on the like a linear profile. This is a linear profile actually. They will vary with the linear profile. So, but my bottom value will be the what I'm putting right now here in the panel. Okay, and secondly, whenever you go through some subject theory work in your career, like fluid dynamics, in your undergrad or your master's or PhD,
Yeah.
people teachers will always tell you that they will take care of the different non-dimensional numbers like Reynolds number. Here maybe Grashof number is there, maybe the Rayleigh number is there, Prandtl number is there, Mach number is there. So what does it mean? It means that they define the flow characteristics. Okay, if these numbers are meshed, then the our Michael your flow and my flow or somebody else flow in some other part of the world, they will have the similar behaviors. Okay, let's say if I make a Reynolds number, what the Reynolds number contains? Reynolds number contains the density, velocity, diameter, or length, whatever the characteristic length is, that the viscosity. It contains the first the fluid properties. So it is now taking out the fluid properties effect. Okay, this essentially means that if you are matching Reynolds number, it means that you are taking out the effect of the fluid properties. Secondly, the velocity, which is the flow property. So you are taking out the effect of the flow property from your simulation, from your experimental work or my experimental work or my simulation. Then we have the diameter. That is a geometry property. So you are also taking out the geometry effects from there. So geometry is smaller. I'm not talking about shape. Shape will should remain same. I'm talking about, and even their their ratio of the parameter should remain same. For example, length to diameter, it should remain same. I'm saying that your geometry is bigger or smaller, it doesn't matter. Your flow properties, they have any properties like a velocity is higher or lower, doesn't change, doesn't matter. Your flow properties varies, doesn't matter. Until that the combination of these four parameters, they give you same Reynolds number. Then your drag coefficient for your aircraft, for my aircraft, if the Reynolds number is same, we should be able to get the, now I'm not talking about the shape of the aerofoil is different, and that's the different story, but same aerofoil shape, but the only coordinate is different. The condition in which they are this is flying is different, velocity is different, but drag coefficient should be exactly same. I'm not talking about drag value, I'm talking about drag coefficient. Non-dimensional values should be same. Dimensional values will vary definitely. For large craft, drag force will be higher. For small craft, drag force will be lower, but drag coefficient will remain same. If you measure the non-sum, that's the point here actually. Okay, this is the whole story. Okay, so this answered your question.
Yeah, that does. Yeah, thank you.
Okay. Okay, so now if you want to like you cannot see the residual plots here. So if you go back to residuals and simply click on the plot, you will see the how they are like behaving. So like the residual plots, they are showing the values are very low actually. Okay, even with the turbulent model. So it depends on the your mesh also. Okay, so we solved the energy equation, we solved the two turbulence equations, we solved the three momentum equations, x, y, and z component, and we solved the mass conservation means continuity equation here. Okay. Now save your file, case and data file both at the same time. It should be done from time to time. Okay. Now what I'm going to do is that now I'm going to compare the few things here. Okay. Before I go to the case, I will discuss about the few things here. So what first is the Prandtl number. So it's a ratio between the momentum transport and thermal transport capacity of the fluid. Okay. So if the Prandtl number is higher than the one is means that the both effects are exactly balancing each other. Okay. At that point, my velocity boundary layer momentum and the thermal boundary layer will be exactly same of the same size. As the my Prandtl numbers is increasing, in that case, the my momentum boundary layer will be thicker than the my thermal boundary layer. It means that the thermal boundary layer will be thinner and the momentum or the velocity boundary layer will be thicker. Okay, and reverse will be case when the Prandtl number is less than the one. Okay, so now the definition, if you like put the drive the equation, you will get the Prandtl number as the viscosity of the fluid, not the viscosity of the something else. Okay, so whenever I talk about the convection, it is like it first cell will be conducting from the surrounding wall, then it will be like a through convection. Okay, here K is also the thermal conductivity of the fluid, not the that wall or that surface. Okay, so this is all about the what is happening with the first cell. The conduction is taking place from the surrounding solid body, and then because the velocity is zero on the very first cell, first molecule, first layer, and then it will transfer to the like surrounding through the convection. Okay, so that's why this is a ratio between momentum transport and thermal transport capacity. This is that through diffusion, and this is through the force convection. Okay, so the Cp is also the fluid and K is also of the fluid. So we put the viscosity as a 0.001 Pascal second. Cp we reduce from the 4148 to the 3000 to so that the we can like we will not be having the like a more temperature transfer to the fluid, but other I want to see something temperature change in the wall as well. So that's why I reduce the capacity to 3000 and I increase the thermal conductivity to 1.5 so that we can have the more heat transfer to the like water as well. So this combination gives me the Prandtl number 2. So you can see the definition here. Now, Nusselt number is a dimensional number that is measures ratio of the convective heat transfer to the conductive heat transfer. This is between the momentum transport and thermal transport, Prandtl number. And this is Nusselt number, same thing. It's about the heat transfer, but the ratio of convective heat transfer to the conduction heat transfer. Okay. So convection heat transfer is the H delta T. I'm not talking about the area because capital Q divided by area is a small q, which is the watts per meter square. And thermal conductivity, again, area is here, so, but we divide and we get the Q conductivity, small q. So the ratio of convection heat transfer to the conduction heat transfer, if you put these values, you will get the HL upon K. This is Nusselt number, or Nusselt number. Sometimes people say Nusselt number, or sometimes people say Nusselt number. Okay, so it's HD upon K. H is the is the convective heat transfer coefficient, K is the thermal conductivity heat transfer coefficient, D is the diameter of the pipe. Okay. Then for comparison purpose, we have the very well-known empirical formula that is called the Dittus-Beotler correlation, and it's an equation used to calculate the heat transfer in the turbulent flow through the smooth pipes. Okay, not the rough pipe, but through the smooth pipe. So it does not take care of the rough pipes. So for rough pipes, there are some other relationships you can see in the like fluid dynamics books. So it is used for designing the heat exchange and cooling systems. It's a very well-known formula. Okay, so we use the for this formula. Okay, this formula is used when we are going to use the CFD calculations. For theoretical empirical formula is this one. So 0.02 into Reynolds number power 0.8. So Reynolds number is the 10,000 for this case. Power 0.8, and then we have the Prandtl number power 0.4 because this is heating the fluid. This is heating the fluid. So we have the more heat transfer from the wall to the fluid. So this is heating the fluid. So 0.4. So we put the Prandtl number was like calculated was 2. So put the Prandtl number is equal to 2 and power n is equal to 0.4. So Nusselt number is equal to 48. This will be constant throughout the pipe. Okay, this will be constant throughout the pipe. This is the point of the having the same area. Okay, this will be constant value, but it will vary with the Reynolds number. Okay. So now we have the Nusselt number here. Now we are going to find out it is from the CFD. So this CFD convergence is like shown here. Now this is a very important concept that we have to see the mixing cup temperature. I discussed that thing. It's a temperature if I get that one volumetric section, and I put that all fluid in the one adiabatic mixing cup and mix it out. So I get the one temperature. That is the bulk temperature. Okay. So how to find out this one? So this bulk temperature is the heat transfer through the that particular mass divided by the what is being stored there. Okay. So I can write it down with the integration sign we discussed day before yesterday. So we get this formula. Now see, this formula actually in the Fluent, if I write it down this formula in this way, this is the my U into T dA and divided by area divided by the this U. This U is actually is the average velocity and that particular plane. Okay, through the cross section, this average velocity at the plane. So this is equal to this 1 upon A integration sign dA of any variable. This is equal to the area weighted average. In Fluent, you will see the function area weighted average. So you have to find out the first, you have to make the function for U and T, velocity and temperature, and then just use the from surface integral area weighted average, and you will get the this whole thing here. Okay. So then simply get the area weighted average for the velocity also, and then divide them together. Like you don't need to multiply with the area because this area is now here. Okay. So get this from the Fluent and this also from Fluent, divide them together, you will get a TB. Okay. And TS also is on the surface temperature. I will get it from the Fluent as well. So I can write it down the H as the Q upon A into TS minus TB. Now Q upon A is the heat transfer, heat flux, which is in our case the 5,000 watt per meter square. So now put the value of surface temperature, bulk temperature, and you get the heat transfer coefficient. Now from heat transfer coefficient, from heat transfer coefficient, I can write it down. Nusselt number is equal to heat transfer coefficient. D is a 1 and K of the fluid in our case is a 1.5. So we are getting Nusselt number is equal to 45.03. This is from CFD. This is from the CFD, and 48 is from the from the Dittus-Beotler correlation or empirical formula. Okay, so just compare them. So how much error you are seeing here now? So if you compare them, we are getting the error of the only 6.818%. This is with the coarse mesh, 48,000 cells only. Okay, so let's do it on the on the Fluent. Okay, so any questions? Okay, so and now, but this is a locally transfer coefficient. So this is only on the one location. So for second location for this pipe, this will be same, but For example, just the Nusselt number is changing along the like a pipeline. In case of, for example, it is same. So you have to find out the Nusselt number heat transfer coefficient in different locations. Okay, then you can plot with acceleration with respect to the heat transfer coefficient Nusselt number. Okay, so first thing is that display the mesh. Okay, go to the view menu, compose, and wall heated. So just make them transparent. Okay. Second is unheated wall, that is front, like in the beginning. So again, the same thing we're going to do here. Okay, draw the one plane, mid plane. Okay, isosurface, and so just we are analyzing some fluid flow. Then I will go with the heat transfer calculations. So the mesh and constant x value, and click on create. Okay. Draw the velocity vectors with the value of 0.4 and on this plane. Okay. Okay. So again, we can see the same results are there. Okay. So delete, and same result we saw in the previous case. Okay. Okay. If you like color by them with temperature, so you can see that the temperature in the middle is like the same, but on the sides is a high temperature. Okay. It varies from 361, and in the middle, this temperature is the 288 Kelvin. Okay. So what we are going to do is that we are going to actually, now this is not only for the only this line section, but on the complete plane. Okay. The complete plane inside in this area in and there's any location. So yes, it's only for turbulent pipe flows. It can be like a modified to be used for the different, anywhere you see the pipe with a turbulent flow, you can apply that one. Okay. So here you can see that with high temperature here and low temperatures are here. Okay. So every temperature, that's what we're talking about is the T bulk or the T mean temperature that we are trying to find out here. Okay. And also we are trying to find out the surface temperature, T surface. That's on the pipe wall. Okay. But on the same, it should be on the same location as well. Okay. So what I'm going to do is that I'm going to from results, create a one plane, and that plane I will be creating close to the end. Okay. So let's make it pipe length is 25, 5 meters upstream, and then the 20 meters for the heated pipe. So I'm going to select my mesh, and this is going to be the Z coordinate. And let's make it like you compute. So this is the 25. So let's make it plane is the 24 meters. Okay. So surface, and we are 24 meters. Okay. Click on create, and then I'm going to create the one line here. Okay. So I have to choose the wall heated so that I can create only, because this plane, if I create the isosurface and this is only on the surface, this will create a line from that surface. Okay. So here I'm going to put the Z line and at location of 24.24. Okay. 24, sorry. 24 meters. Okay. So click on create. Okay, if we display these values, you will see that this is actually is over here. The surface is here, this surface, okay? This is the cross-sectional area actually and on this location. And if we talk about the line, this line is here, okay? So again, use the compose menu and simply like delete the surface. So line is here, you can see, okay? You can change the color of the line as well. So by type, and if you go to the surface and put the color as a green, let's say, okay? So you can see the now green color line here, okay? So Z surface here and then the line here, okay? So what I'm going to do is that I'm going to make my function. That function is only velocity into time, into temperature, okay? So first select the velocity, select, then multiply, and then the temperature, select. So say this is my velocity temperature function, okay? Click on define. Okay, so I will go to the results, and from here I'm going to click on the surface integrals. Okay. So area weighted average. So I told you that the area weighted average means that this is equal to this integration. So you take the two variables like through defined user defined function. So like a u into t, and then when you say you area weighted average, this is equal to integration sign dA upon area. Okay, so integration of the dA means that this is complete area of that particular internal surface. So if you divide by the area, you will get the answer is equal to 1. So what actually we are getting is that we are getting the average value of the velocity into temperature. Now, if I divide that average velocity and temperature by the average velocity, what I'm going to get, I'm going to get the average temperature. This is actually a point of this whole exercise. Okay. So here what we get, we have the like elevated average velocity into temperature on the surface. Okay. So the value is the 3.009. Okay. Then I'm going to get the velocity on this location. Okay. This was the multiplication of velocity and temperature. This is going to be the only velocity here. Okay. Velocity only. Then I will go to the vortex average, and I'm going to take this line only. Okay. And I will get the wall temperature. I will get the wall temperature here, and that's on the line, this line. So this complete line around the circular path. So average line will give me the averaging whatever will give me single value that's representing the wall temperature on this whole location. Okay. So surface temperature on this location is the 360.43699. Okay. So put these values here. So I put the value as 3.009 for the integration, divided by the average velocity, which is the 0.01056. If you run the case for the more iterations, the value will be refined to the 0.01056. Okay. Similarly, the surface temperature I got was the 360, same mesh, 360.5352. So if you run the case for the more iterations, you get this value. Okay. Then after we have done with Fluent results, we got the results from there. Now we use our formulas. So H is Q upon small q upon Ts minus Tb. So Q is the 5,000 watts per meter square. And if you put the value of the Ts, which is 360.5, and the Tb is a 286.55. So what we get the convection heat transfer coefficient H. For Nusselt number, this will be the HD upon K fluid. So this is equal to 67.58 into 1 divided by 1.5. And this is the case where we are running the case coarse mesh with the 0.1 million cells. It's a hexa meshing y plus less than 1. And we are using K epsilon Laswell model. Okay, you can use the SST model as well. So we get Nusselt number is equal to 45.03. And if you remember that we got the Nusselt number from the Dittus-Beotler correlation as the 48. So now just get a percent difference here. So we get the error of only 6.18%. Okay, 6.18% only. Now this is we run the case. I ran the case for the different conditions, but that is without UDF, and the length were different. It was for the air properties. But I don't think so that the value should change. If the Reynolds number and Perron number is same, then this graph should be followed. Okay, the graph should be followed. But definitely the Prandtl number is different, Nernst number is same, but Prandtl number is different. That's why at 10,000 the value of the Nusselt number is 35. It varies definitely. Okay, so if you want to plot a similar plot, then you have to run the cases for different Nernst numbers. Okay, different Nernst number. Then only thing you have to change is the every time you will be seeing the different velocities. Okay, so you have to put that velocity in the UDFs. Okay, every time you get the different every velocity, so you have to go back and just modify your UDF. Okay, where's the UDF? This one. Okay, so let's open the with Notepad++. This one. So you have to vary the your V average here every time. That's the only thing. Okay. So compile the new UDF, apply that on the inlet condition, run the case, and you should be able to get the new Nusselt number. And then you should be able to draw these Nusselt numbers in this way. Okay. So any questions, any feedback or anything? This is now end of the course here. Anything you want to contribute or you want to ask here?
Hi, Sichal. So I have two questions, and so
Yes.
the first one is that the dissolved, what do you call it? The Dittus, oh, the sorry,
Dittus-Beotler.
the yeah,
Dittus-Beotler.
Dittus-Beotler, yeah,
Yes.
yeah. So is that only for the internal flow like this?
You
For
part for the pipe flow.
pipe flow? Okay.
Like a
Yeah.
means when you say pipe flow means that anything like a there looks like a pipe, this will fit here. Okay, so pipe flow like now I will always find these pipes here, but the heat exchanger shell and tube heat exchanger, it's kind of the
Oh,
like
okay.
pipes are there. You can see the ducts in the your HVAC system, cooling system. You see inside the your car, inside your car engine bay, you see the pipes there. So everywhere you will see the pipes, and you will be should be able to apply the this Dittus-Beotler correlation.
Oh, okay. Uh, yeah, and one more question is, let's say, for example, with this particular scenario, how would you go about and do, let's say, one-way FSI? So that means, let's say, you transfer this data into FEA.
Yes, for one-way FSI, what I will be doing is that I will be running this case in the workbench. So, if you want to gain this experience, so I would suggest one thing, that the cooling tower FSI. Okay.
Oh, okay.
So this is actually this is through the AI overview on the Google, but the figure that you are seeing here is a figure is from the Maya simulations.
Oh,
Okay,
okay.
this is the like a one course and mastering as a CFD level 1 on the Udemy. So it contains the like this is like a same like the thing you're asking here. Okay, so here you can see this is like a one-way FSI. Get the load from the CFD and then we run the circular analysis. Okay.
Oh, okay. So
Here you can
with this
see.
one, can you is that done using ICEM or ANSYS meshing?
No, no. This was done, I think, through the maybe ICMCFD tetra meshing or maybe the
Oh, okay.
workbench meshing. Okay, but
Right. Yeah.
it doesn't matter actually. There are different meshing softwares. If you're able to get the good mesh, then it doesn't matter. But if you are definitely with the good softwares, you should be able to get the better mesh. Okay, ICMCFD has more control now. Nowadays we have the fluid meshing also. Workbench meshing should also be very decent for the people are starting their career in the CFD. But the point is that whatever mesh is that mesh can be
Oh, okay. So fluid meshing is also compatible with this, isn't it?
the inside we have the like
For CFD.
separate inside for fluid dynamics we have the mesh in the fluid region in the for structure we need to have the mesh inside the solid bodies. Okay,
Okay.
so they don't need to be compatible. They can be different.
Oh, okay.
Okay, so see this is like you can see the original boundary was here. This is deformation is this much deformation is taking place here, and why this is so? Because there is an air load. It's coming from the left side. Okay, is it
Oh,
deforming
okay.
there? So now their deformation, this one deformation maybe is like a very exaggerated, but actually if you take a look on the scale here, so 10 power minus 6, 10 power minus 6 scale, it is showing you because of the way it is showing you, but if you take a look on the values here, you see there's a 10 power minus 6. Who cares? 10 power minus 6.
Yeah.
Okay. So you can like, I think that this link is given there. Even we have the like a heat exchanger course, you can take the link from here. This case is in the mastering answer CFD level 1. Okay.
Okay.
So I will share you the link in the WhatsApp group. Okay.
Thank you.
So now any feedback? How was the course? It was useful or not? Did you learn something new, something advanced, like a Y plus calculator, UDF, applying the boundary conditions, applying the different customized fluid properties, then applying the like Y plus values, these conditions, then get the like this data with the custom field functions, and then finally calculate the heat transfer coefficient, then the Nusselt number. It was like some advanced thing for you. It was a very common thing for you. So do give me the feedback, okay? Okay, so then now we are going to officially conclude the course here, and thank you for your time and your patience and your learning eagerness. This was very nice to see. Okay, see you then again on the some other courses. Okay,
Okay. Thank you.
thank you, bye bye.